Throughout the experimental synthesis of benzyl acetate, the differentiating characteristics that were used were the density, which allowed substances that had a higher density to move to the bottom of the beakers, which allowed for the separation of the substances, the polarity, which allowed for certain substances to mix and other substances to remain separated, and the color after separation, which allowed us to differentiate between the different layers. Chromatography was used to determine the purity of the final substance. Gas chromatography works by a sample being vaporized and then moved through a column containing the stationary phase, and the substance is then separated into its individual components based on its interaction with the stationary phase. In our experiment, our gas chromatography only had one peak, which means that the substance that we synthesized only had one component. This means that it is a pure substance. Spectrometry is another method of analyzing the final substance that we employed. Mass spectrometry determines the chemical makeup of a substance by its separation of ions that make up the substance. The ions are separated by their masses and their charges. In our experiment, the mass spectroscopy compared with the sample mass spectroscopy for benzyl acetate shares the same distinctive peaks. They both have a peak at 150, 108, 90, 80, 65, and 43. Another experimental analysis that we performed on the benzyl acetate that we synthesized was infrared spectrometry. Infrared spectrometry analyzes the types of bonding present in the molecule by analyzing the stretching and bending and other types of movement that occurs on the molecules in relation to the various atoms within the molecule. The way this works is that a sample is run through the infrared spectrometer, and then it records the infrared light absorbance versus the wavelength. This is the absorbance that occurs at specific wavelengths based on the structures present in the molecule. These absorbances are resonant frequencies that match the vibrational frequency of the molecule. This means that the type of wavelength that is absorbed determines what the substance consists of, and the types of bonds that are present as a certain type of bonds absorbs specific types of wavelengths. In the experimental application, the infrared spectrum was created. Analysis of the infrared spectrum revealed peaks at the interaction of the benzyl ring, the C double bond O bonds, and the CH and OH bonds that are present in the benzyl acetate. The final test that was run on the synthesized benzyl acetate was nuclear magnetic resonance spectrometry, or NMR spectrometry. The nuclear resonance spectrometer records the number of hydrogen atoms present in each molecule. It also elucidates the chemical environment of the hydrogen atoms. The shift, delta, on the x-axis indicates the hydrogen atom's proximity to functional groups. In the experimental analysis, the position of the peaks almost exactly matched the theoretical position of the peaks on the graph. Next, the number of peaks is analyzed, as the number of peaks minus 1 equals the number of hydrogens on neighbor atoms. All of the peaks are singular, implying that there are no neighboring hydrogens. Finally, the integration is analyzed. The integration is the area under the peak. The values are not whole numbers, so we will convert them to whole numbers by dividing all of the numbers by the smallest integration value. We then have peak ratios of 2.46 to 1 to 1.58. These are not whole numbers, so we will have to multiply the values by 2 to get whole numbers. This equals 4.9 to 2 to 3.16, giving a slight experimental error. We can round these to whole numbers, which would result in 5 hydrogen atoms in group A, 2 in group B, and 3 in group C. This matches with the number of hydrogen atoms in the benzyl acetate molecule. The intermolecular forces present in the solution change the interaction that the substances have with each other. Benzyl alcohol and acetic anhydride would not typically mix on their own because benzyl alcohol has hydrogen bonding and would not interact with acetic anhydride, which only has dipole-dipole interactions. This is because like interacts with like, and these two are not like in their intermolecular forces. This means without a catalyst, the benzyl alcohol would be more attracted to itself than it would be towards the acetic anhydride. Sulfuric acid has 2 points for hydrogen bonding and also has double bonded oxygens that would attract both benzyl alcohol and acetic anhydride together. Because the substances do not mix on their own, it has a lower potential energy in the unmixed state. The addition of sulfuric acid has the substance overcome the potential energy and helps mix the substance, which is a higher number of configurations but also a higher potential energy. The molecular interactions exhibited in the substances resulted in the ability to separate the substances. The interactions between the substances caused solutions of different densities to form. The partial unmixing of the solutions caused a denser solution to form that allowed for the waste to be removed. The idea that like would only interact with like resulted in the separation of nonpolar non-ionic substances that was the benzyl acetate. Intermolecular forces also came into play in reference to the magnesium sulfate as it absorbed the polar water but not the nonpolar benzyl acetate. This allowed the mixtures to be separated out from each other. In the experimental synthesis of benzyl acetate, the reactants were benzyl alcohol and acetic anhydride. These formed benzyl acetate and acetic acid. The catalyst for this reaction was the sulfuric acid. After the initial reaction, we added a half-saturated sodium chloride solution to our substance. The sodium chloride interacted with the polarity of the acetic acid. This created a substance that was more energetically favorable to be mixed yet separate from the benzyl acetate. This substance has a higher density than the benzyl acetate and settles to the bottom with a visibly distinguishable result. The bottom layer was then transferred to a waste beaker. So sodium bicarbonate was added to the substance to neutralize the remaining acetic acid. The neutralization resulted in the formation of water, sodium acetate, and carbon dioxide. The top waste layer was then discarded. The sodium chloride washes were then repeated from the beginning. The sodium chloride and the sodium acetate would mix together and form a higher density solution that is favored by potential energy to not have the benzyl acetate in it. This is because sodium chloride and sodium acetate are both salts, whereas benzyl acetate is not. When left to unmix, it is possible to transfer this water out of the bottom of the beaker, at which point the sodium chloride wash was repeated another 2 more times. Once with a half-saturated mixture and once with a fully saturated mixture. At this point, the mixture should be only benzyl acetate and water. Magnesium sulfate was then added to absorb the water from the mixture. The magnesium sulfate and the water were then filtered out, leaving only the benzyl acetate as the final product. Once the benzyl acetate had been fully synthesized, it was important to determine the purity of the result. The purity is the amount of the desired reaction product to the amount of the product mixture. It is typically represented as a percentage of the product in the product mixture. Purity equals desired reaction product divided by product mixture times 100%. Then when purity is calculated, it can be combined with the amount of product to get the actual amount of product. Actual amount equals purity divided by 100 times measured amount. To find the desired reaction product in the product mixture, a graph chromatography is needed. The desired reaction product is the area of the peak caused by the product, and the product mixture is the sum of the area underneath all of the peaks. In our experiment, the gas chromatograph had only one peak, meaning that we had 100% pure substance. Then, because our 100% purity, that means that our actual amount is equal to the measured amount of the substance. Product yield is a calculated value representing how much of the product that was produced compared to the ideal amount that should have been obtained. The product yield percentage equals the actual amount divided by the ideal amount times 100. In our experiment, for every mole of benzyl alcohol and acetic anhydride, the reaction would ideally produce 1 mole of benzyl acetate. In our experiment, benzyl alcohol was the limiting substance because there were only 0.0211 moles of benzyl alcohol and there were 0.0317 moles of acetic acid. With this, we should have had 0.0211 moles of benzyl acetate, and we produced only 0.0042 moles of benzyl acetate. Our product yield was 19.68%.